Hello, and welcome to my presentation for Cosmology at Home. Today I will be talking a little bit about some research that I have done over the last few months, some of it in lockdown. And I will be talking a little bit about an alternative model for the early universe, that is a bouncing model, which has gained some interest over the last decade or so. And I will be discussing some effects that incorporating viscosity in our cosmology could have for such an alternative. So without further ado, let's get into the outline of my talk. I will be talking a little bit about what is kind of mainstream to describing our early universe, the theory of inflation or the paradigm of inflation. Then I will be talking about one alternative to the paradigm of inflation, that is the bounce. And for most of this talk, we will be discussing what is one of the main problems that plagues a bouncing universe scenario, or rather a scenario which incorporates a contracting phase. That is a problem of growing anisotropies. And in this spirit, I will present ekpyrosis, which is a mechanism that has been used in the bouncing cosmology community to deal with this problem of growing anisotropies in the contracting phase. Then I will incorporate viscosity to essentially show that shear viscous stresses is an alternative way that we can use to isotropize a contracting universe as it approaches the bounce. And I will show that this is true for the most general anisotropic cosmologies. And finally, I will be presenting my conclusions. Now, this picture may or may not be familiar to a lot of you. It represents the history of the universe as we know it right now. We are, of course, in the far right of the picture. We're in a dark energy dominated phase. But I will be talking mostly about the far left of this picture. In this picture, it shows some sort of a Big Bang event, followed by a period of what is called inflation. Now, cosmological inflation hypothesizes a period of accelerated expansion driven by a scalar field in the very beginning of the universe. The good thing about this is that it explains things like the large-scale isotropy of the universe today. It does this by redshifting away energy densities in the anisotropies very, very quickly. It is also able to explain the horizon problem, where seemingly causally disconnected patches of the CMB sky now come into causal contact because of this period of cosmological inflation. And so it would explain why they would be so similar to such high degrees of accuracy. It also predicts extremely small non-Gaussianities, and we haven't really detected non-Gaussianities yet in the large-scale structure in CMB. And it gives us a mechanism for understanding how the fluctuations that seed density perturbations and the large-scale structure of our universe could have originated primordially. So overall, inflation is a very successful paradigm in explaining a lot of the problems of standard cosmology today. But of course, there is always a but. Inflation, despite its many successes, does suffer some issues within the paradigm. For example, there is a lot of controversy on how one can embed inflation, which is technically a toy model or a paradigm, into a high energy theory, such as string theory. There are other issues, such as the issues of initial conditions and how one needs to specify a very particular set of conditions for inflation to occur in the way we want it to. It isn't clear how to exit from inflation. There are issues around the Transplanckian problem, and there's controversy around that. And for me, one of the biggest issues with inflation is that if we hypothesize an ever-expanding universe, singularity theorems, Hawking singularity theorems tell us that we end up in a universe that is past geodesically incomplete, or the Big Bang singularity is inevitable. So all of these issues leads a lot of model building efforts within the inflationary community itself. But it also leads us to look for alternatives. And I think whether or not you want to work in the inflationary paradigm or outside it, it's a worthwhile effort to try to construct alternatives and to pit them against each other to see if we can come up with the same predictions or what the merits and demerits of such alternative paradigms could be, and whether in fact they can be reduced to one another. So in this spirit, one of the paradigms that people have looked into and one that I will be focusing on is the theory of the bounce. So just as a quick recap, we've talked about inflation as a paradigm in which the universe acceleratedly expanded under the influence of a slowly rolling scalar field called the inflaton in the very early universe. This helps us solve problems as a large-scale isotropy, and it tells us about it gives us correct predictions for the CMB and LSS spectrums that we observe, and it also gives us a mechanism, a primordial mechanism for generating perturbations that seed the large-scale structure. Despite this, there are some issues with the scenario, and regardless of anything, I feel that it is important to direct research into constructing alternative scenarios and pitting them against each other, and we're about to discuss one such scenario. The scenario that we're about to discuss is called the paradigm of the bounce. In this paradigm, we hypothesize that the universe gets, at some point, starts out large and cold, and then it becomes smaller. And as it becomes smaller, as it contracts, it hits a minimum size at which some new physics can be injected, which causes the universe to re-expand. Now, the models that I will be interested in, because I'm most worried about the singularity problem, are models where this minimum size is finite and it is large enough to be able to be described by classical physics. So I am interested in models of the bounce that are classically non-singular. Of course, the price we pay for this is that we have to find some new physics to cause the universe to re-expand. But there are some general conditions that even from the level of Friedman equations, we can derive to understand what are the conditions that we need for a bounce to be successful. So I said that the universe starts out contracting. So coming out of the contracting phase, the Hubble rate would be negative. In the expanding phase, the Hubble rate is positive. So in the transition phase, the Hubble rate has got to be 0. So that is our condition 1. H has to be 0 at the bounce. Now we want the universe to re-expand. So obviously we need the time derivative of h dot, to be positive. If we look at the Friedman equations, which I've written there, then we can see that if the spatial curvature is 0, then for h dot to be positive, we need this combination of rho plus p to be negative. That is, we need a null energy condition violation. However, of course, if we have positive spatial curvature, we can have a bounce. So in this vein, there have been some bouncing solutions that have been found in closed radiation FRW universes. But if we want the bounce to occur at a finite volume, then still we require the existence of some null energy condition field or some new ingredient. Good. So for part of my talk, the way I will be creating this bounce is that I'm going to introduce a phenomenological quadratic equation of state, where of course we have the linear term that we're all used to in the ideal equation of state. In addition to this, we have a quadratic term. So the way we modulate this quadratic term is we say that at some high energy scale, rho c, the nonlinearities become important. And when rho is much smaller than rho c, the nonlinear term is no longer important, and this equation of state would act as our usual ideal equation of state. For some part of this work, we ignore the cosmological constant because we're only interested in rho 10 near rho c. And we have this equation of state resembling radiation at its linear level. And we choose beta being this coefficient of the nonlinear term being -1 to make contact with other work that has been done with regard to introducing nonlinearities in the equation of state, for example, loop quantum cosmologies, etc. So in the isotropic Friedman-Robertson-Walker case with closed universes, oscillating solutions have always been found, for example, by Marco Bruni and Kishore Ananda. But for our cases, we are trying to ask the question of what happens to anisotropies in a contracting phase and whether introducing a bouncing mechanism can help the universe re-expand despite being highly anisotropic, or perhaps we need to have the anisotropies taken care of initially. So just to give you a sense of what has been going on in this rather long background, I like to take inspiration from one of my favorite writers, Douglas Adams, And I think he's right when he says that in the early universe cosmology community, we've been arguing a lot. And the story so far is that in the beginning, the universe was created. This has made a lot of people very angry and has been widely regarded as a bad move. So the problem at hand is the question of what to do with anisotropies, which seem to be growing in the contracting phase, and whether they mess up our really neat model of a non-singular bounce and a bounce from which the universe ultimately re-expands. So the question we're asking in this talk is, do anisotropic bouncing cosmologies still bounce, and can they isotropize? Can they give us the isotropic universe that we see today? So just as a quick recap, we've talked about a theory of inflation as being a description of the very early universe, where the universe has become uh, bigger in an accelerated way, mediated by a scalar field. We've emphasized that despite the successes of this paradigm, it is important to look for alternatives, both because there are some inconsistencies within the paradigm, and also because it is in good scientific practice to try to construct alternatives so that we can pit them against each other and see whether which one is better and which one is worse, and hopefully find some observational smoking gun test to differentiate between them. In this spirit, I am discussing one particular alternative that is called the bounce, where a universe that is initially very large and cold becomes smaller and then hits a minimum size, which is finite. And because of some new physics injected at this minimum size, the universe starts re-expanding. The conditions for this to take place is that at the minimum size, the Hubble rate has to be zero, and the rate of change of Hubble rate, h dot, has to be positive. Um, the model that we are going to be discussing for the remainder of this talk is the model of a nonlinear fluid, where we phenomenologically introduce a nonlinear term to our equation of state. And we show that and it has been shown that this nonlinear equation of state, with a particular choice of the parameters, can indeed create a successful bounce in the closed isotropic Friedmann-Robertson-Walker case. And now we are coming to the question of what happens when you start out with an anisotropic initial state. What happens when you have anisotropies in the large universe that begins to contract? Do the anisotropies grow? And if so, do they affect the bounce in some way? And finally, can a bouncing universe indeed isotropize to give rise to the isotropic universe we see right now? So in this vein, we're going to discuss one particular mechanism of isotropization that is used in the bouncing cosmology community called ekpyrosis. In fact, this is the one that is the most widely used, I would say. So to understand what exactly is happening with ekpyrosis, let's take a really simple example. Consider a flat anisotropic universe that is expanding with different expansion rates in the three different directions. So in this regard, we have three different scale factors, A, B, and C, in the three different directions. So the Friedmann equation can be written as some sigma squared, which encodes the energy density in the expansion anisotropies, plus whatever matter fields you may have. Now the evolution equation of the shear is as follows. So this shows that the sigma squared term, which is sigma alpha beta, would evolve as 1 over volume squared. So the idea of ekpyrosis is to effectively introduce some matter field, which they do by introducing a scalar field that is fast rolling down an exponential potential that is able to evolve faster than 1 over volume squared. So this is able to smooth out all of the anisotropies that would occur in the contracting phase. Of course, this is a very simple illustrative example of a universe that is only has expansion anisotropies. Anisotropies can occur in the curvature, and it can occur in the energy momentum tensor as well. So in order to understand what the effect of this ekpyrotic field, this raw matter being going faster than 1 over volume squared is, we turn to the most general class of anisotropic cosmologies called the Bianchi Class A cosmologies. So I can write the generalized metric in this form, where depending upon which specific model we are talking about, the one forms will take different forms. So then we put in an ekpyrotic equation of state, So the ekpyrotic equation of state is one where the energy density will evolve faster than 1 over volume squared. This just means that pressure will be greater than density, or if we write the equation of state as P is equal to gamma minus 1 rho, this would mean that the parameter gamma is greater than 2. Bear in mind at this point, we're not making any assumptions about the constancy of the parameter gamma, and for the remainder of this work, we will not need to. So the results that I will show will apply for non-constant gamma, non-constant equation of state parameters as well. So there's a way to decompose this cosmology in a 3+1 splitting, and we can write out the Einstein's equations on the spatially homogeneous hypersurfaces in all generality for all of these Bianchi Class A cosmologies. So in doing so, we can also reduce the Einstein's equations into a phase plane system by writing them in terms of these expansion normalized variables. So we normalize the energy density with respect to the Hubble rate, and we get omega. We normalize the energy density and the anisotropies with respect to the Hubble rate to get sigma squared. And finally, we have the 3 curvature, which we also normalize with respect to the square of the Hubble rate. In doing so, the set of Einstein's equations reduce to a set of a coupled first order differential equation or ordinary differential equations of the form x prime is equal f of x. And the Friedman constraint then becomes an algebraic constraint because of this expansion normalization process, and they are subject to this constraint. And we are trying to understand what the stability behavior is of the state vector, which is composed of the shear variables and the spatial curvature variables and the density variable. So it has been shown by Litzy back in 2005 that using some simple facts that we know about these universes, that the curvature of the Bianchi type 1 to 8 universes in class A are always negative, imposing that the energy density has got to be positive, and that the condition of ekpyrosis, that is the ultra stiffness, that gamma is greater than 2, pressure is greater than rho, we can prove a general no-head theorem for all the Bianchi types 1 to 8 and separately type 9. I say separately type 9 because type 9, as we will see, has positive spatial curvature, so the process proceeds in slightly differently. But regardless, the conclusion remains the same, that all initially contracting, spatially homogeneous orthogonal Bianchi type 1 to 8 cosmologies and type 9 universes, when they are sourced by an ultra-stiff fluid, that will always collapse to an isotropic singularity. So the sink is a spatially flat isotropic FRW universe. Now I say the word collapse, and we've been talking about bounces. Bear in mind, at this point, we're only interested in what happens to the anisotropies in the contracting phase. To create a bounce, we will need to inject new physics, which is not something that we're talking about in this context right now. But suffice to say that including an ekpyrotic equation of state allows the universe to re-expand. So we now go to an alternative mechanism of ekpyrosis, of isotropization, excuse me. That is the introduction of viscous stresses. And in order to do this, let me first show you what happens when we don't include any kind of isotropizing mechanism in a particular kind of anisotropic universe. And the anisotropic universe that we will be discussing is the Bianchi type 9 universe, which falls under class A. And the reason we're discussing this particular universe is because it contains within itself not just the expansion anisotropy that I used to show you how ekpyrosis works, but also contains within itself anisotropies in the 3 curvature. So the Bianchi type 9 universe also, this universe is interesting because it is used to model the generic approach to a singularity. So an anisotropic universe, when it's contracting and gets very close to a singularity, would be expected to follow this geometry. And the other reason it's interesting is that it shows chaotic behavior in the form of infinite chaotic oscillations in a finite time interval when the lower limit of this time interval is 0. Of course, by including some sort of a bouncing mechanism and a non-singular bounce, the lower limit of this finite time interval is no longer 0. So we get rid of this problem of infinite oscillations. But there's another way to mitigate this chaotic behavior, but more on that in a little bit. In the meantime, even when we include the nonlinear equation of state with this bouncing mechanism, with this new physics in it, we see that the same chaotic oscillation that are ubiquitous in Bianchi type 9 is present, is even with the incorporation of this nonlinear equation of state. Now, if we include a shear viscous term, which is a term that acts as an anisotropic pressure, but has a very specific form, which is being proportional to the anisotropies themselves, but the proportionality but the coefficient of viscosity, the proportionality, being dependent upon the energy density itself. That is, being dependent on rho to the power of half. If we do this, then we see that actually including the shear viscosity makes including the shear viscosity makes the shear anisotropies decrease. And we see this in the normalized anisotropies, and which the peaks of these anisotropies start to decrease. We can further see this by looking at what happens to scale factors in the type 9 universe that we were discussing, and we see that the chaotic oscillations cease and they become more isotropic. In fact, we even find by calculating the Lyapunov index that the chaotic behavior is mitigated. So this makes us hopeful, but that's just one type 9 universe that we have discussed, the effect of shear viscosities. We can ground this with even more strength by proving a new no-hair theorem, using similar conditions as we did in the previous case of the no-hair theorem that was proved for ekpyrosis. And using a similar procedure, we can show that assuming that the curvature of type 1 to 8 universes in class A being negative, imposing the positivity of the energy condition, also imposing that the matter obeys a strong energy condition, we find a condition on the coefficient of viscosity, the constant term kappa that we showed. If this kappa is greater than 3 into 2 minus gamma, where gamma is the equation of state parameter, then we can prove another new cosmic no-hair theorem for viscous cosmologies. And we say that all class A cosmologies, which are sourced by a fluid obeying the strong energy condition, and which incorporate a shear viscous term acting as a negative anisotropic stress, will obey the condition and in which the coefficient of viscosity kappa obeys this condition, can collapse into an isotropic singularity. This is us not including some mechanism for the bounce, but enough to say that we don't need to depend on ekpyrosis to create isotropization. Incorporating a shear viscosity for the most general anisotropic cosmologies do lead us to similar conclusions around isotropization. Again, these results hold for the most general equation of state parameters, which do not need to be constant. So finally, the take home is that we don't need to have a Big Bang singularity as the end of our story. Non-singular cosmologies can be used to describe a very early universe. Another way to have a bounce and a non-singular bounce is to use nonlinear fluids. And another way of dealing with one of the most pernicious problems in bouncing cosmologies, in contracting universe, that is the problem of growing anisotropies, is to include shear viscous effects. And we have shown that these shear viscous effects in the most general anisotropic cosmologies are successful in isotropizing the contracting phase. Thank you very much.